Good morning, students. So today we will go for experiment number 2, which is network theorem 2. And objective of this experiment is to verify Norton's and maximum power transfer theorem. So in this experiment, we look upon on two theorem. First, Norton's theorem, and then maximum power transfer theorem. So what we'll do, we'll go for one circuit, and there we'll try to prove the Norton's theorem is also valid and maximum power transfer theorem also valid. So first we look upon on some apparatus that we'll use in this experiment. So first thing, this is a completely DC experiment. So for this experiment, we obviously need some kind of source. So here left hand side a DC source has been shown. So you can see there are several knobs. First is power knob, so you have to switch on that power knob to get the supply. Then there are two, one is voltage knob, one is current knob. These two knobs are for, first one is for voltage, means constant voltage, constant current supply, so the current will be constant and we can increase the voltage value of the source. And second one is for constant voltage mode, where we fix the voltage and we will increase the current one. So, and there are another three knobs that is for the connection of the wires. You can see one is positive, one is negative, another is ground. The ground one must be used, and we can use either positive one or negative one depending upon we need positive voltage or negative voltage. According to that, we can select. Okay. So for our experiment, we'll select the ground knob and the positive one. Okay. In the second side, we can see there is one multimeter. It is called multimeter because multiple thing can be measured. So once we give DC supply, we have to measure the output voltages and output current in several resistances. So that we'll see later. But how to measure the voltage or current? We can see there is one knob. So by this multimeter, we can measure both AC and DC voltage and current. So according to that knob, you have to select what you have to measure. You have to measure DC voltage, DC current, or AC voltage and AC current. Accordingly, you have to move the knob. Okay. And what will be the range? And there are three connecting knob. We can see one is 10 ampere, one is common, and another is from voltage one. So common one will be always used. Now we can connect either 10 ampere if you have to measure very high amount of current, or we can connect to the voltage one if we have to measure low amount of current and some voltages or some resistances. Then we have to connect in the another port. Okay. Now these two are two voltmeter has been. So voltmeter means it will measure the voltage. So if some places we need the what is the voltage, we have to look upon, then we have to use this instrument. So it can be either analog or digital. In our lab, we will see both. So in digital, it will be directly given how much voltage is there. Is analog, you have to measure by yourself. If you see the analog one, we can see there are four connecting knobs. So we have to connect one connection at the 0 1, and another connection we can connect either 3 volt, 15 volt, or 30 volt. They have given for larger scale. And so why they have given? Because if you have to maximum measurement is our 3 volt, and if we connect to the 30 volt knob, then it will give result, but the result will be not precise. Okay, so that's why if we know that our maximum voltage will come 2 volt or near about 3 volts, so we'll go for the 3 volt one for more precise reading. According to that, 15 volt and 30 volt knob can be used. Okay. Now these are some ammeters. So again, here we are using the DC ammeter. Again, DC ammeter can be analog or digital, and you can see these two type of ammeter in our lab. Again, digital ammeter will directly give what is the result, and analog for analog you have to see by yourself. And in analog there are external knobs where we have to connect and according to your scale, how much current you need to measure, according to that you have to connect. Okay, so these three things we'll need for our experiment. That is, first one DC source, then DC ammeter, DC voltmeter, and one multimeter. Okay. Now we'll come to our our main experiment. So first we'll go for Norton's theorem. So if we see what is the theory of Norton's theorem. So what is Norton's theorem? Norton's theorem is for solving some kind of DC circuit. So if there is a complex DC circuit, that DC circuit can be replaced by some other things. So that we'll see in Norton's theorem. So what does Norton's theorem say? It is said that any two output terminals of a linear active network containing independent sources may be replaced by a current source and a parallel resistance. So that figure has been shown here. We can see the circuit at figure 1. This is a complex bridge circuit which consists of ABCD bridge, and the load is between C and A, that is the RL. RL is the load resistance. Now this complex ABCD circuit can be replaced by a equivalent current source as has been shown here, that is ISH, and a parallel resistance, that is RL. So that is Norton's theorem, that any complex circuit can be replaced by an equivalent current source and a resistance which is in parallel with that equivalent current source. Now, how to measure that equivalent current source and the parallel resistance? That is the question. So from Norton's theorem, it has been said that and another important thing, that Norton's theorem is only valid for linear active network, and the circuit should contain only independent source, no dependent source. Okay, so here in this circuit we can see there is only one independent source, that is VA. Okay, now we'll come how to measure the equivalent current and the parallel resistance. So the magnitude of that current source, that means that ISH here, that magnitude of the ISH will be equal to the current measured when the load terminal is short circuit. So how to measure ISH? What we have to do here, between A and C, there is the load, that is RL. So what we have to do, we have to short circuit between C and A, and we have to put some ammeter and we measure the short circuit current. So it is said in Norton's theorem that the short circuit current between C and A here, that will be equal to this ISH. And what is RL? RL is the parallel resistance that has been connected for the Norton's theorem. And how to calculate RL? RN will be the equivalent resistance of the circuit looking from the load terminal with all independent sources replaced by their internal resistance. So what is RN? RN is, we have to open circuit RL, and from there we have to see by replacing V in with their internal resistance, and we have to measure the resistance, and that will be RN. So there are several steps. I'll go step by step for better understanding. So what if we go for Norton's theorem and we have to replace the complex network by a current source with a parallel resistance? So how we can do that? So what is the first step? The first step is we have to disconnect the load resistance. So here what we have to do, we have to disconnect the load resistance between C and A, and we have to short it. Okay. Now again we have to redraw the circuit with each practical source replaced by their internal resistances. So what we have to do here, we have to replace the V in with its internal resistance, and we have to measure what is the total impedance or what is the total resistance of the circuit from the load side, that you have to see, and we have to measure RN. Okay. So we have already got so we have already got RN, that is the equivalent resistance of the circuit. Now what we have to do, we have to measure the short circuit current, that is ISH. Now we have already got ISH, we have already got RN, so we can draw this circuit, that ISH and the RN will be parallel to that. Then what we have to do, we have to again reconnect the load, that is RL, and we can measure the current. We can measure the power, we can measure the voltage, we can measure the current at the load side, and that will be the actual circuit output, load voltage, load current, and load power. So what does Norton's theorem say? That Norton's theorem said that this figure 1 and figure 2 are the same circuit, but accordingly we have to measure the ISH and RN. That is the Norton's theorem. Okay. So how we are going to prove the Norton's theorem in our lab? So first, what we'll do in our lab? In our lab, there are 4 resistances, that is P, Q, RS will be given to you, and accordingly we can connect them like this for a bridge circuit. Now, once the bridge circuit is completed, one source, voltage source will be given to you, and you have to connect that voltage source with the bridge circuit, and a load will also be given, where the load will be variable load. So we can vary the load from minimum to maximum or maximum to minimum. And the load will also be connected between A and C terminal, just shown here. Okay. So first, what is the first step? First step is we'll fix the input voltage. The input voltage is fixed. What we are varying? We are varying the load, that is RL. So RL will vary from minimum to maximum, and we'll put one voltmeter and one ammeter at RL, and by the voltmeter we'll measure the load voltage, and by the ammeter we'll measure the load current. So what we are doing, we are varying the RL from minimum to maximum value, and with that we are measuring the all voltages and all current for different RL value, and we'll plot them in a graph. Like here it has been shown that IL will be in the y-axis and VL will be in the x-axis. So we'll take different resistance value. At the load side, we'll vary the resistance, and accordingly we'll measure the VL and IL, and we'll plot them like this. Okay. So one graph we'll get from here. Now, if figure 1 and figure 2 are the same circuit, then the graph that is obtained from figure 1 and that graph is obtained from figure 2 will also be same. Now we'll see what graph we'll get from figure 2. Now figure 2, our circuit is like this. So there are 2 parallel elements. You can see one is Rn and another is RL that are parallel to ISH. Okay. Now if we try to find out what will be our IL, from the equation we can get one equation, that what will be our IL and what will be our VL. So first thing first, that we have taken that the voltage, the load voltage is here also VL for the second case. Okay. So if load voltage is VL, then how much current will pass through Rn? The middle one, the middle resistance, that is Rn. How much current will pass? Suppose we take that current is I1, and I1 will be equal to how much? Load voltage you have taken as VL, so I1 will be equal to VL by RL. So how much current will be IL? IL will be ISH minus I1, that is passed through RL. So it will be obviously ISH minus VL by RL. So if from this equation, if we try to plot this equation, we'll get this graph where in the y-axis, we can see in the y-axis where it is cutting the y-axis, it will be the total intersection will be ISH. We'll get from the equation, right? IL will be equal to ISH minus VL by RN. So what will be the slope? The slope will be minus 1 by RN. And what will be the intersection in y-axis? That will be ISH. Now what is ISH? ISH is the short circuit current, where here C and A are short circuited. The load are short circuited, and accordingly we can calculate what is ISH. Now Norton's theorem will be valid when this figure 1a and figure 3 are same. Now we don't get figure 3, we'll get figure 1a. Figure 1a we have already got. How? We are varying RL, and with varying RL we are measuring VL and IL, and we are getting this graph. Now what we can do with this, we can short C and A, right, by some wire. Practically we can short C and A with some wire, and we can connect one ammeter there, and we can measure what will be the short circuit current between C and A. Like this circuit, we can see here this circuit between C and A, it is shorted, and some ammeter is placed to measure ISH. So we can measure ISH here. And the thing is how we are going to measure RN. We are going to measure RN by this. Here we can say RN is, from the second table we can say RN is VOC by ISC. Now what is VOC? VOC is the, sorry. Yes, what is VOC? VOC is the open circuit voltage of the two terminal and ISC is the short circuit current. So RN we can directly calculate by dividing VOC by ISC, or RL we can calculate by using some multimeter also at the load terminal. Okay, so what is the equivalent resistance? So to find out the equivalent resistance, we can go in two way. Either we can directly connect a multimeter, or otherwise we have to measure the open circuit voltage here. So to measure the open circuit voltage between C and A, what we'll do, we'll just connect one voltmeter. Voltmeter has very high resistance, so it will be almost like an open circuit and it will measure the voltage. So once we'll get the VOC, that is the open circuit voltage at load, that is between C and A, and the short circuit current between C and A, we'll just divide the open circuit voltage by short circuit current and we can get R. So up to now, what things we have got? We have got this graph at figure 1a by varying VL and IL. We have got ISH value. What is the short circuit current value? That ISH value. And we have got the RN. So from this graph, if we see that our Y intersection, after plotting this IL versus VL graph, if we increase that graph in both x-axis and y-axis, where it will be cut the y-axis and x-axis, and if we measure how much current is at y-axis from this graph figure 1a, and if we compare that to ISH, that is the short circuit current, and if the value are matching, that means yes, Norton's theorem is okay, because this 1a graph and this figure 3 graph, they are matching with each other. So first thing is we'll calculate ISH and we'll try to compare that ISH with Y intersection. Now second thing, we'll measure RN and we'll try to find out what is minus 1 by RN, and we'll try to see that minus 1 by Rn is matching with this graph slope or not. The slope of this graph should be minus 1 by Rn. So that is how we are proving Norton's theorem. So we'll go to the procedure again, then it will be easier. So I am just summarize things. So we'll plot VL versus IL by changing RL. We'll get this graph at figure 1a. Then what we'll do, we'll short circuit C and A terminal and we'll measure the ISH value and we'll compare the ISH value with the Y intersection. And if it is comparable, then the Norton's theorem is okay. Then second thing, we'll measure the RN, that is the equivalent resistance. And after measuring RN, we'll see the slope is minus 1 by RN on. Okay. So that is the thing. If these two are matching, then Norton's theorem is valid. So we can change this circuit in figure 1 to the circuit in figure 2. Okay. Now what will be the procedure? Again I am describing what will be the procedure for. So first, set up the circuit. So we have to set up the bridge circuit ABCD first, and we can use either the highest value or the lowest value of RN. Now what will the next step? We have to switch on the power supply, and the input voltage, that V in, that will be a fixed value. Okay. So suppose here it is taken as 10 volt. We can take some other value like 20 volt also. Doesn't matter, but it has to be fixed throughout the total experiment. Now next thing, what we have to change the RL value, and by using some ammeter, we are measuring the VL and IL value of the load. Okay. Now we'll plot this VL versus IL. Okay. So how we'll gradually either increase or decrease RL till the lowest supply value is exhausted. And for every RL, we have to measure the VL and IL. Now finally, VL and IL will be plotted, and the intercept ILO and slope M will be find out that how much is the Y intersection and what is the slope. Now again, what we'll be doing between C and A, we'll put 1 milliammeter as has been shown in figure 5. So to measure the short circuit current. So ammeter has very less amount of resistance, so it will be almost like a short circuit, and we'll measure the short circuit. And now again, we can measure the RN, that is the that is the equivalent resistance of the circuit by a ammeter, by a multimeter, or by measuring the open circuit voltage and dividing the open circuit voltage with the short circuit current. Okay. And we'll find out that ILO will be equal to ISH. That means the y-axis intersection will be equal to the short circuit current and the slope will be equal to 1 by R. This will verify the Norton's theorem. Okay. Now here a observation table has been given and we can see that we have taken the load resistance first 3.2 ohm and we are gradually increase the load resistance up to 100 ohm. And according to that we are measuring the load voltage and load current. And with this, so what will be the student work? First you have to plot this load voltage and load current in one graph, and according to that you have to find out what is your y intersection and what is the slope. And this has been already given, the open circuit voltage, short circuit current and RN value. So this short circuit current value ISC, this is also measured, and this is a example of the observation table. So the open circuit voltage and short circuit current has been given. So the Y intersection will be equal to the short circuit current, that is 0.057, and the slope should be 1 by RL, that is has been given here. Okay. So this is student work. So to verify Norton's theorem, you have to plot the graph, and according to you have to find out the intersection, and you have to see that it is matching with ISC or not, and the slope is matching with 1 by Rn or not. Okay. So Norton's theorem is completed. Now we'll come to maximum power transfer theorem. Now what is maximum power transfer theorem? If you see the theory, maximum power transfer theorem states that to obtain maximum amount of power from source, the resistance of the load must be equal to the resistance of the internal resistance of the circuit. So what is that maximum power transfer theorem? Is said that the circuit will deliver maximum amount of power when the load resistance will be equal to the internal resistance of the circuit. So we have already measured, when we are going for Norton's theorem, we have already measured what is the internal resistance, what is the what is the equivalent resistance of the circuit. We have already measured. Suppose that is, we have already got, that is Rn. Okay. So here for this experiment that is given as RO, but RO and Rn are equivalent. Okay. Now what does this experiment say? That if we change the load from minimum to maximum value, then from there we can get one load resistance where we will find out the maximum power the circuit will deliver. So if we decrease from that load resistance, we'll get less amount of power. If we increase also, we'll get less amount of power. Like this graph here has been shown, we can see it is the y-axis is the total amount of load power and x-axis is the load resistance, and we can see at R0 the maximum power is achieved. So if we go left from the R0, we'll get less amount of power. If we go right, we'll again got less amount of power. So that is maximum power transfer theorem, that it said that at a certain resistance, load resistance value will get the maximum amount of power, and the certain load resistance will be equal to the equivalent resistance of the circuit. Okay. So how we are going to prove for this experiment? So I'll see the procedure. So we are taking the same circuit, same bridge circuit that we have taken for Norton's theorem. So what we are doing, you can see in the figure, we are connecting one ammeter and one voltmeter at the load, so we can measure the load current and load voltage. Okay. So what now we are going to do? We are giving some supply and we are varying the load from minimum to maximum, and according to that we are measuring the load current and load voltage by the ammeter and voltmeter. Now once we get the load voltage and load current, and as it is a resistive load, so we can direct multiply the current and voltage to get the load power. So for different resistance value, we get the current and voltages. So we get the different load power for different resistances, and we plot them. And by plotting, the plot will come like this, here shown in the figure 2. and we'll get one certain point where we'll find out the power will be the maximum. And that point, if we measure what is our resistance will be R0, and R0 will be equal to RL. That is the equivalent resistance of the circuit. If we can do this, if we can vary the load resistance, and accordingly we plot the load resistance versus the load power curve, and we'll get what is the maximum power. And at that maximum power, if we try to find out what is our load resistance, we'll see that this load resistance will match with the internal resistance, and that will prove the maximum power transfer theorem. Okay, I am telling again what we are going to do. We are varying the RL from a minimum to maximum value, and according to that we'll measure the load voltage and load current. From there we'll find out what is our total load power, and we'll just plot them, the load power and the load resistance, in a single graph, and from there we'll find out where the maximum power is happening, and according to that we'll find out what will be the resistance, and that resistance should be equal to the equivalent resistance of the circuit. Okay, so this is the procedure. So first we'll set up the same circuit, and we'll give the we'll switch on some power supply source as Vin. Now this Vin will be fixed throughout the experiment. So you can take suppose 10 volt, and we'll fix that throughout the experiment. Now we'll insert a resistance that is at the load, that is RL, and we'll measure the load voltage and load current as has been shown here with a voltmeter and an ammeter. Now we'll just increase the load from minimum to maximum, and then again from maximum to minimum. So for each resistance value we'll get 2 voltage and 2 current values. So what we have to do, so for that, just give me a minute. So as we are getting 2 load voltage and 2 load current, so what we have to do, we have to average that for every reading. Okay, so instead of that, you can do that, we can only increase in this experiment, we have only increased from minimum to maximum value. Okay, and we'll find out what is the voltage and current. Now once the voltage and current has been find out, we can find out the total amount of power, and we have to plot P versus RL, and from the graph we'll find out what is the RL value at which the power is maximum, and this RL value will be equal to the internal resistance value, or RN value, or RO. So which is verify the maximum power transfer theorem. Okay. Now here is one observation table has been given for the student. So what does student have to do? Student have to calculate the what is the total amount of power from VL and IL, and according to that we can see several RL values has been given, which is increasing from a minimum value to a maximum value. So what does student have to do? Student have to find out what is the power for each RL value, and they have to plot in one graph paper the load power in the y-axis, and in the x-axis that will be the resistances. So we'll find out what is the maximum amount of power, and from the maximum amount of power we'll find out what is the resistance for which is causing the maximum amount of power, and according to that we'll find out the resistance, and we'll compare the resistance with our internal resistance that we have already find out. Here we can see our internal resistance is 40.35, and it will be find out that the maximum power transfer will occur only when the resistance will be equal to that 40 point something that internal resistance value. So that will prove the maximum power transfer. Okay, so in this experiment we have discussed 2 things. First, how to verify Norton's theorem. Second, how to verify maximum power transfer theorem. And we'll find out that the Norton's theorem is also experimentally verified, and maximum power transfer theorem also experimentally verified. Okay, so thank you very much. I'll stop here.